Let me first thank the organizers for putting together this very nice conference and for the opportunity to speak here. Today I'm going to talk about directed distances in bipolar-oriented triangulations. So this will be part of a joint work with Jacopo Borga, and it will also be part of a somewhat coordinated pair of talks. So Jacopo is speaking next on a closely related topic. OK, so I'm sure most of you already know what is a planar map, but just in case, let me review the definition. So a planar map is just a graph embedded into the plane, viewed modulo orientation preserving homeomorphisms from the plane to itself. OK, random planar maps are of substantial interest in probability theory, in part because they can be viewed as discrete analogs of Liouville quantum gravity. So Liouville quantum gravity is a one-parameter family of models of random fractal surfaces. In this talk, we're not going to need a lot of detail about what is the definition of Liouville quantum gravity. So I'll just leave it there for the time being. And then these pictures on the left, this is a picture of a random planar map. And then this is a picture of a large random planar map, which has been drawn in three-dimensional Euclidean space in such a way that the edge lengths are as close as possible to 1. This can be kind of viewed as a visual representation of one of these Liouville quantum gravity surfaces. OK. So there's a one-parameter family of these Liouville quantum gravity surfaces. They're indexed by a parameter gamma between 0 and 2. And the parameter gamma depends on the type of random planar map under consideration. In particular, uniform random planar maps, they should all converge to Liouville quantum gravity with parameter gamma equal to the square root of 8/3. So this includes also uniform planar maps with local constraints, like uniform triangulations, where all of the faces are required to have degree 3, or quadrangulations, where they are required to have degree 4, and so forth. Okay, and this type of convergence has been rigorously established in a bunch of different senses. Okay. Other values of gamma are believed and in a few cases proven to describe the scaling limit of various types of decorated random planar maps. Okay? For example, if we look at planar maps decorated by spanning trees, so we sample a uniformly random pair consisting of a planar map and a spanning tree on it, then the underlying planar map is believed to converge in the scaling limit to one of these Liouville quantum gravity surfaces with parameter gamma equal to the square root of 2. So let me emphasize here that the planar map is not uniform. Rather, planar maps which have more possible spanning trees would be more likely to be seen if we sample the planar map in this manner. In a similar vein, planar maps decorated by the Ising model are expected to converge to Liouville quantum gravity with parameter equal to square root of 3. Especially relevant for this talk, planar maps decorated by bipolar orientations are expected to converge to Liouville quantum gravity with gamma equal to the square root of 4/3. So I'll say momentarily what is a bipolar orientation. But first, I want to say a little bit more about kind of what is actually known about the large-scale behavior of various types of random planar maps, just kind of by way of context for our main result. Okay, so there is a huge literature concerning graph distances in uniform random planar maps. Okay, so here graph distance is just the distance between two vertices, is the shortest path of edges joining those two vertices. In particular, for a uniform planar map, or for a uniform triangulation or quadrangulation or what have you, with n edges, it's known that the graph distance diameter it scales like n to the 1/4 as n goes to infinity. Okay, so a map with n edges typically has graph distance diameter of order n to the 1/4. Furthermore, it's known that the scaling limit of uniformly sampled planar maps with n edges, when you rescale graph distances by n to the negative 1/4, if you take the scaling limit with respect to the Gromov-Hausdorff topology, you will get a random metric space called the Brownian map. Okay? So this is a rough random fractal metric space. It's homeomorphic to the sphere, but has very different geometry. Okay, and there's been extensions of this to various other Brownian surfaces with different topologies and various other classes of random planar maps, and so forth. And it was proven by Jason Miller and Scott Sheffield that the Brownian map is in fact equivalent as a metric space to this one of these Liouville quantum gravity surfaces with parameter gamma equal to the square root of 8/3. Okay, so this is kind of can be viewed, the combination of these two results can be viewed as a kind of a rigorous statement to the effect that uniform random planar maps converge to Liouville quantum gravity with gamma equal to the square root of 8/3. Okay, but the proofs of these results about graph distances in uniform random planar maps, they all rely crucially on what's called the Schaefer bijection, which is a way of encoding a uniform sampled random planar map in terms of a tree with labels on its vertices. Okay, and here the labels exactly correspond to graph distances in the random planar map. And so this encoding is very convenient for analyzing graph distances. Okay. But in contrast, for non-uniform random planar maps, there is no analog of the Schaefer bijections. There's no bijection where graph distances are encoded nicely. And as a consequence of this, graph distances in decorated random planar maps are much less well understood than in the case of uniform random planar maps. Right? Now, it's believed that graph distances in these decorated planar maps should grow like n to the power 1 over d sub gamma, where d sub gamma is the Hausdorff dimension of the Liouville quantum gravity metric space. Okay? So if you have one of these planar map models that's supposed to converge to gamma LQG, for example, these spanning tree decorated maps with gamma equal to square root of 2, then the graph distance diameter of a map of size n, it should behave like n to the 1 over the dimension of the square root of 2 Liouville quantum gravity metric space. But for gamma not equal to square root of 8/3, this number d sub gamma is not known. And computing it is like one of the biggest open problems in the subject of Liouville quantum gravity. Okay. In some cases, it's actually possible to prove rigorous versions of this up to a little O of 1 error in the exponent. So this can be done using some quite sophisticated Liouville quantum gravity machinery. But there are no scaling limit results for non-uniform random planar maps. And this distance exponent is not known explicitly. Okay. Any questions on this before I start talking about what we're able to prove? Okay. So in this talk, I'm going to focus on bipolar-oriented random planar maps. Okay. So let me say what that means. So a bipolar orientation on a planar map is an acyclic orientation on the edges, meaning there's no directed cycles, which has a unique source. There's only one vertex where all of the edges are outgoing, and a unique sink. There's only one vertex where all of the edges are incoming. I think I have the source and the sink definition reversed here, but I think you can get the idea from the picture over here. So the source, all of the edges are going out. The sink, they're all coming in. And all of the other vertices have at least one incoming and at least one outgoing. Okay. Now, bipolar-oriented planar maps are kind of a natural model of directed planar maps. So planar maps where you have not just edges, but you have a direction associated to each of the edges. And furthermore, these bipolar-oriented planar maps are to some extent tractable, because they can be bijectively encoded by what's called the Kenyon-Miller-Sheffield-Wilson, abbreviated KMSW, bijection. So I'll say more about this bijection a little bit later. But basically, this is an encoding of a bipolar-oriented planar map by means of a random walk on Z2, wherein each step of the planar map, or each step of the walk, corresponds to an edge of the planar map. Okay, so it gives you kind of a way of exploring this whole planar map one edge at a time. But in contrast to the Schaefer bijection, it does not give any kind of nice description of graph distances. Okay. So these bipolar-oriented planar maps, they're known to be in the square root of 4/3 LQG universality class. So they're believed to converge to LQG with parameter equal to the square root of 4/3. Let me note this is different than square root of 8/3. So they're believed to have very different large-scale behavior as compared to uniform random planar maps. And it's known it's known thanks to like LQG techniques that the undirected distance exponent for bipolar-oriented planar maps is 1 over the dimension of square root of 4/3 LQG. Okay, so it's known that this exponent exists, but it's not known what is its value. Okay, and to clarify, this means if we sample a uniform bipolar-oriented planar map with n edges, then the undirected graph distances scale like n to this power. Okay. But since this is a directed random planar map, in addition to just looking at undirected graph distances, it's also natural to consider directed graph distances. Okay? So in particular, we can look at the shortest directed path between any two vertices, which I'll abbreviate SDP of x comma y. So this is only defined if there actually is a directed path between x and y. Because we're looking at these directed distances, it's also interesting to consider the longest directed path from x to y. Okay, so we have two different notions of directed graph distances on a bipolar-oriented triangulation. And we can think of these directed graph distances as kind of like random planar map analogs of directed first or last passage percolation. So you're looking at longest or shortest directed paths in this directed random environment. Okay? And I'll say more on this analogy a little bit later in the talk. There's lots of parallels between directed distances in planar maps and directed first and last passage percolation. Okay. Just like undirected graph distances in one of these planar maps can be viewed as like a discretization of the undirected LQG metric, these directed graph distances we can think of as a discretization of a hypothetical directed square root of 4/3 LQG metric, which has not been rigorously constructed yet, but maybe will be within the next few years. Okay. So this is how you define directed graph distances. And the main result that I want to discuss today is that in apparent contrast to undirected graph distances, directed graph distances in bipolar-oriented triangulations are kind of exactly solvable. So you can actually get formulas, you can compute things explicitly, you can get explicit scaling limits for lots of observables, and so forth. So this is kind of the rough summary of the main results that I'm going to present. Not only are directed distances in these uniform bipolar-oriented triangulations solvable, but we have kind of a general technique for analyzing directed distances in various kinds of random planar maps, which also applies to a bunch of other different planar map models, including planar map models in other universality classes. Maybe if you saw Yuan Zheng's poster, you saw a little bit on this, and then Jacopo's talk will also discuss some other models to which our techniques are applicable. Okay, I now want to give a more precise presentation of our main results. Okay, so we're going to start by looking at the uniform infinite bipolar-oriented triangulation, which is the Benjamini-Schramm local limit of a uniform bipolar-oriented triangulation with n edges around a uniformly chosen edge. Okay, so it's maybe you guys have seen like the UIPT, like the uniform infinite planar triangulation. This is the analog of that for bipolar-oriented triangulations. Okay? And it's not too hard to show that this exists using the encoding by random walk.
So what happens then with the sources and sinks? Do they somehow disappear?
Yeah, so that it's an infinite directed planar map. It has an acyclic orientation with no source or sink. we can think of the source and sink as being kind of at infinity in this map. Okay.
So, sorry to interrupt.
Yeah.
Another question. What is actually the continuous analog, if you think in terms of vector fields?
Continuous analog in the continuum. What is the analog of the orientation? I will say more about that a little bit later on. But basically, what it is you have a coupled pair of SLE12 curves, okay, such that they're coupled together so that in some sense the angle between them is pi/2, okay, and then a path is directed if it is hit in order by both of the two SLE12 curves. Okay, so this is kind of what should be the continuum analog of this orientation. Okay, so it's a little bit subtle to actually define this, and it's not just like the naive thing that you would think where the orientation is the one that you inherit from R2 or something like that. Okay, but for various reasons, that's kind of the natural way of defining directedness in the continuum setting. Okay. On this UIBOT, we're going to need to look at a kind of natural interface, which is defined in the following way. Okay, so we're going to look at this root edge E0, and we're going to look at the rightmost directed path started from the terminal endpoint of E0. Okay, so what that means is we start at this vertex, we look at the outgoing edge, which is furthest to the right, okay, and then we look at the outgoing edge, which is furthest to the right from the next vertex, and so forth. Okay, and that defines us the rightmost outgoing path, which is shown in red here. Okay. We're also going to need the leftmost incoming path. It's defined in a similar way. We start at this vertex. We look at the leftmost path, leftmost incoming edge, and then we take the leftmost incoming edge from the starting endpoint of the next vertex, and so forth. Okay, and that path is shown in dashed red. Okay, so we have these two directed paths to infinity. And we're going to define m sub 0 comma infinity to be the submap of the UIBOT, which lies to the left of this rightmost outgoing path and to the left of this leftmost incoming path. Okay, so it's kind of like this m0 infinity. It's like covering about half of the UIBOT. Okay. And we declare that edges on this blue path, this rightmost outgoing path, are part of m0 infinity, but edges along the red path are not. So that's why I drew the blue path as a solid line, but the red path as a dashed line. Okay. So this definition, it might look at first glance, a little bit strange. Like why do we define this map in exactly this way? But basically, this map is natural because it corresponds to the submap, which is explored after time 0 when you do the KMSW encoding of this map. It's also the discrete analog of the stuff explored after time 0 by an SLE12 curve from infinity to infinity. Okay, so it's kind of the future part of M. Okay. And we're also going to let, so this is a conflict of notation, or no. So I'm going to let xk for k and z be the boundary vertices of m0 infinity enumerated from left to right. Okay. So everybody clear on these definitions?
Can you say again what it is in terms of SLE12?
So you take an SLE12 curve from infinity to infinity in the plane. Okay. And you parameterize it so that it hits 0 at time 0, right? So it's going from like R to R2, hits the origin at time 0, and then you look at the stuff which is visited after time 0. Okay, so it's like the future part of the SLE12 curve. Make sense? All right. So the first result that we prove gives the existence of the Busemann function for directed distances along this interface. Okay, so what is the Busemann function? Well, heuristically speaking, it is the function x of k, which is defined to be the length of the longest directed path from xk to infinity minus the length of the longest directed path from x0 to infinity. Okay, of course, this does not make rigorous sense because both of these distances are infinite, right? You can have a path of infinite length going from any vertex to infinity. But it can be made sense of by taking limits. Okay? Or equivalently, this Busemann function can be made sense of using coalescence of geodesics. So roughly speaking, so basically what we prove is if we take the leftmost LDP geodesic going from x0 to infinity and the leftmost LDP geodesic going from xk to infinity, then these geodesics will eventually meet and stay together thereafter. Okay? One can then define the Busemann function to be the length of like the right boundary of this geodesic slice, the length of the right boundary of so the segment of the geodesic from x0 before they meet, minus the segment of the geodesic from xk before they meet, minus the segment of the geodesic from x0 before they meet. Okay, so one can define the Busemann function in this way. And it's it's non-trivial. These geodesics actually do coalesce, but we do prove that, and that allows us to show that this Busemann function exists. Okay. So Busemann functions have been kind of extensively studied in the setting of first and last passage percolation, but to our knowledge, this is the first study of these things in the setting of directed random planar maps. Okay. So our first main result, it gives the scaling limit of this Busemann function. Okay, so what we show is that in the case of longest directed paths, if we take our Busemann function, we scale time by k, we scale space by k to the -3/2, then it will converge in law to a 2/3 stable Lévy process. Okay, to be a little bit more precise. Along this, the Busemann function along this blue boundary, so for the Busemann function for positive times, converges to a 2/3 stable Lévy process with only downward jumps. And along the negative part of the boundary, it converges to a 2/3 stable Lévy process, which is symmetric, so it has the same rate of positive and negative jumps. Okay. And then in the SDP case, we have a similar result, except you instead get a 4/3 stable Lévy process. All right, so we get the scaling limit of the Busemann function for directed distances along this interface in the UIBOT, and kind of the big thing that we'd be missing to get kind of a full scaling limit result for this whole directed random environment would be to understand kind of the joint scaling limit of directed distances along different interfaces, and that we don't understand yet. We just know the scaling limit along this single interface. Okay. So maybe are there any questions on this Busemann function stuff before I talk about our next main result? Yep.
So in the proof, do you couple the paths?
Do we?
The two orange paths, is it a coupling argument in the proof?
To show that they coalesce?
Yeah.
So it's actually a little bit simpler than that. We show that there's an infinite sequence of maps, or infinite sequence of points in the map, which in fact every directed path has to visit. So it's kind of like cut points for the purposes of directed paths. Okay, and that of course forces a coalescence. Other questions on this? Okay. So in addition to these results for the uniform infinite bipolar-oriented triangulation, we also prove some results for finite bipolar-oriented triangulations. So here is a sort of informal statement of our result in this setting. So we show that for certain models of finite bipolar-oriented triangulations with n edges, the longest directed path distances are comparable up to constants to n to the 3/4 And the shortest directed path distances are comparable up to constants to n to the 3/8. Okay. So that in particular, we prove this for like Boltzmann distribution on bipolar-oriented triangulations with boundary length n to the 1/2, and for size n KMSW cells. We expect that our results could also be extended to uniform bipolar-oriented triangulations with boundary length with n total edges, but that would take a little bit more technical work, and so we decided not to do this in our first paper. Okay, so so we get these kind of these scaling exponents for directed distances in finite bipolar-oriented triangulations, and we can think of these as being sort of the directed analogs of the reciprocal of the LQG dimension, this 1/d sub square root of 4/3. Okay, because we know that this is the scaling exponent for undirected distances, and now we have now we know the scaling know explicitly the scaling exponents for directed distances. Okay. And a very interesting open question is to determine some sort of exact limiting law for some distance observables in these finite triangulations. So at this point, we only know up to constants estimates, which can give tightness of some observables. We don't know the exact limiting law of any observables on finite bipolar-oriented triangulations. Okay. So questions on that? All right. So I want to next say a little bit more about kind of the parallels between directed distances in bipolar-oriented triangulations with directed first and last passage percolation. For concreteness, I'm going to focus on last passage percolation, but most of what I say also works for first passage percolation. Okay, so to define last passage percolation, we're going to assign IID weights to the vertices of the first quadrant in Z2. And it's kind of conventional in this setting to rotate things by 45 degrees. So the first quadrant is drawn like this. Okay. And last passage percolation, it considers the highest weight, paths with the highest total weight, which go only in the north direction. Okay, so they're only allowed to travel upward. All right. Now, it's known, thanks to kind of a large body of work in the first and last passage percolation literature, that this last passage percolation is sort of integrable when the edge weights have an exponential distribution. Okay, so in that case, you can get a bunch of you can get like exact laws for some of these last passage times, and you can also get you can construct the Busemann function. You can show that it has independent increments, and so forth. So we can kind of think of these exponential LPP distances as like a lattice analog of directed distances in a bipolar-oriented planar map. Let me emphasize that in the bipolar-oriented planar map, we do not need to put weights on the edges, because the underlying graph itself is random, and so you get interesting randomness just coming from the shape of the planar map. Okay, so in this exponential LPP, you can get these n to the 1/2 and n to the 1/3 scaling exponents for different observables for passage times. And that's kind of analogous to in our setting, we get this n to the 3/4 scaling exponent for directed distances in the bipolar-oriented triangulation. Let me emphasize that in the bipolar-oriented triangulation, kind of the first order stuff already has the first order randomness is already interesting, whereas here it's like the second order fluctuations. The first order is deterministic, and it's the second order fluctuations where you see interesting randomness. Okay, so in this directed first and last passage percolation, a natural like interface to consider is a horizontal line. And kind of in our setting, this horizontal line is kind of analogous to this, this interface that we considered before. So this interface, which is the union of the rightmost outgoing and leftmost incoming path for a given edge. Okay. So in last passage percolation, it's known that the Busemann function converges to what's called the stationary horizon, which is a coupled family of Brownian motions. Just sort of plays a role analogous to the stable process, which is the scaling limit of the Busemann function in the random planar map setting. But kind of in contrast to the case of last passage percolation, in the random planar map setting, there's sort of only one direction that you can approach infinity from. Okay, so there's not like different possible directions for geodesics. So there's really only one Busemann function, instead of like this coupled family of Busemann functions like what one has in LPP. Okay, and it's for directed last passage percolation. It's believed that the fluctuations should converge to what's called the directed landscape, which is this object in the KPZ universality class, and that plays a role kind of analogous to this the square root of 4/3 directed LQG metric. So it's kind of the should be like the full scaling limit of directed distance. And then kind of the big thing that's sort of missing in our setting as compared to the KPZ setting is that it's known that the time evolution of the Busemann function. So if you look at the Busemann function on different horizontal lines and you shift the location of the horizontal line, then kind of the change in the Busemann function is governed by kind of a variational problem involving the solution to the KPZ equation. But we don't have the analog of this for square root of 4/3 LQG. So we just know the law of the Busemann function along one interface. We don't yet know how the Busemann functions on different interfaces are coupled together. Okay, and determining this coupling seems to be kind of super interesting because it looks like we're trying to find sort of some alpha stable LQG analog of this this KPZ equation. Okay, so is there questions on just this kind of this whole analogy to LPP? Yeah.
So in the beginning, you mentioned there is a random walk bijection for this bipolar.
Yeah.
Do you think that's possible for you to construct this analog of the KPZ equation in this case?
You mean like can the random walk bijection be used to construct like the analog of it? Well, I mean, it is certainly possible that would be useful for this purpose, but at this point we don't know how to do it.
Do you have other result for the for other parameter other than the square root of 4/3 LTG?
Yes, we do, and that will be the topic of Jacopo's talk. All right, so I want to say now a little bit about kind of the main ideas of our proof. So I'm not going to go into any technical detail. There are lots of technical details, but I want to highlight what are kind of the two key ideas that allow us to actually analyze these directed distances. Okay. So the first crucial input is independence of geodesic slices. Okay, so to explain this, let's suppose that we start with a Boltzmann bipolar-oriented triangulation with given left and right boundary lengths. Okay, so we're fixing the lengths of the boundary arcs between the source and the sink. But the total number of edges of our bipolar-oriented triangulation is random and is sampled according to a certain special probability distribution. Okay. And let's look at the leftmost directed geodesic between the source and the sink. Okay, there could be more than one path of the same length, but if there is, we just pick the one that's furthest to the left. Okay, and then it's not too hard to see, just using some elementary combinatorial arguments, that if we condition on the length of this leftmost geodesic, then the submaps of our bipolar-oriented triangulation lying to the left of the geodesic and lying to the right of the geodesic are conditionally independent. And in fact, they're uniform over all of the different possibilities, subject to having this length for the geodesic. Okay. So this orange geodesic, it divides the map into this yellow and blue submap, and those submaps are independent from each other, conditional on the length of the geodesic. Okay, and the same is true both for longest and shortest directed paths. Okay. Now, using this plus a non-trivial amount of work, we can show the following thing. So if we look at this map M0 infinity, and we look at the directed geodesics started from all of the different boundary points and going to infinity. Okay? These directed geodesics, they divide up the map into a bunch of slices. Okay, so slices are the regions between the geodesics. And what we show is that these slices are independent. Okay? So in particular, this implies that our Busemann function has independent increments. Okay, which is analogous to what's shown for like exponential LPP. All right. Furthermore, we can also show that all of the geodesic slices along the right half of the boundary have the same law, and all of the geodesic slices along the left half of the boundary have the same law. Okay, so this implies that the Busemann function sort of almost has stationary increments. It's just that the positive time increments all have the same law, and the negative time increments all have the same law. Okay. So we get this independent stationary increments property for the Busemann function. Okay, which is a nice thing to have. It gives us quite a bit of integrability. But just this independent stationary increments for the Busemann function doesn't let us actually compute anything, right? Because we need to know something about the law of the increments. Okay. To get the law of the increments, we use the following strategy. So because we know the increments are independent and stationary, we know that the whole law of the Busemann function is totally determined by just two functions. So the first one is the law of the Busemann function at time -1. So that's determining the law of the negative time increments. And then the law of the Busemann function at time 1, that's determining the law of the positive time increments. Okay. And we also have this KMSW bijection, which gives us a way of exploring our whole map one edge at a time. Okay. And it's known that the law of the UIBOT is kind of stationary under the KMSW procedure. So you do one step of this KMSW bijection. So you're kind of moving the root edge one unit forward. It gives you a new rooted map with the same law. Okay. And we know exactly what is the procedure to get from like the time 0 map in the KMSW procedure to the time 1 map in the KMSW procedure. So there's just 3 possibilities. We do each one with probability 1/3. So with probability 1/3, we shift the root edge 1 unit to the right. With probability 1/3, we add a new triangle, and we make its left edge the new root edge. And with probability 1/3, we add a new triangle which has two edges on the boundary, and we make its non-boundary edge the new root edge. Okay, and then in each of these pictures, like this time 1 map M1 infinity, it's just the gray shaded region. Okay, so we have a very explicit kind of stationary Markovian procedure for building this map. Okay. And in particular, the Busemann function on this time 0 map has the same law as the Busemann function on the time 1 map. Okay, because we know this KMSW procedure is stationary. Okay, so that leads to a recursive equation satisfied by these laws f and g. Okay, it's a kind of ugly recursive equation because you have to take like max and min of stuff when you're trying to write the time 0 Busemann function in terms of the time 1 Busemann function, but you can write it down. You get some recursive equation.
Is this recursive equation the same as the recursive equation for LPP?
No, it's quite different from the recursive equation that you would see in LPP. Okay. Yes, you have this recursive equation, and from this we can convert this recursive equation into a functional equation satisfied by the characteristic functions. So these are the characteristic functions of the distribution of the left increments and the distribution of the right increments. Okay. So we get some complicated functional equations satisfied by these characteristic functions. Then what we do is we kind of expand everything to first order in this functional equation. We do some fairly complicated computations, and we're able to get the kind of the leading order behavior of these characteristic functions as t goes to 0. Okay. Then if you know the leading order behavior of the characteristic functions as t goes to 0, you can use a Tauberian theorem to get the leading order behavior, to get like the tail behavior of the distributions of this x of -1 and x of 1. Okay, so you get the tail behavior of the Busemann increments. And then if we know the tail behavior of the Busemann increments, and we know the increments are IID, then we can get the convergence to a stable Lévy process by like standard heavy-tailed central limit theorem. Okay, so this is the kind of key ideas in the proof. There are many technicalities which I'm glossing over, but hopefully this gives you an idea of what we do. Okay, so questions on these proof ideas? So in the last few minutes of the talk, I just want to briefly touch on some future directions, some of which you'll hear more about in Jacopo's talk. Okay. So first of all, like our same sort of general strategy of showing like the independent stationary increments for the Busemann function, and then analyzing this recursive equation. Works for a bunch of other models. Okay, so we can do bipolar-oriented. So we can do like a weighted version of bipolar-oriented triangulations, which you'll hear about from Jacopo momentarily. You can do shortest directed path hit in order by the contour exploration in a spanning tree decorated map, which you maybe saw in Yuan Zhang's poster. We think we should be able to do the shortest path hit in order by an interface and a planar map decorated by the Fortuyn-Castelline model. So this is a work in progress. We should be able to do shortest directed path in planar maps decorated by Schneider-Woods, and maybe also bipolar-oriented maps with other face degree distributions. And there's probably other models that our techniques could apply to. We're still working and figuring out like how general this technique really is. And kind of another thing that connects to what we did is longest increasing subsequences in various types of random permutations. So several kinds of random permutations that are connected to these directed distances in random planar maps. I want to highlight in particular that the longest increasing subsequence in uniform Baxter permutations is exactly the same as the longest directed path in a bipolar-oriented map with a general face degree distribution. Okay, so kind of like these longest increasing subsequence in Baxter permutation is very closely related to directed distances in bipolar-oriented planar maps, analogously to how like longest increasing subsequence in uniform permutation is related to directed distance in KPZ universality class. So if we could extend our techniques to bipolar-oriented maps with a general face degree distribution instead of just triangulations, then we would get that the longest increasing subsequence for a uniform Baxter permutation grows like n to the 3/4 as well. Okay, so my time is fairly limited, so I think I'm not going to be able to to get into too much detail about some speculative things about the full scaling limit. But I do want to maybe just briefly show this kind of diagram of the different models that we look at. So we kind of conjecture that there should in fact be a two-parameter family of models of directed LQG metrics. So one parameter is just this LQG parameter gamma, and then there's this other parameter theta, which is kind of controlling like how much constraint do you put on the direction that paths can go in. Okay, so theta equals 0, it just means the path can only follow like a single SLE kappa curve, and then theta equals 2 pi. It corresponds to undirected distance, so no constraint on the direction that paths can travel in. So we have, so in blue are the models in this family where we actually know how to compute the directed exponent and also get some scaling limit results. And then we believe that there's kind of this one parameter family of models, so this one-dimensional curve in parameter space where stuff is sort of more integrable. In this curve, it includes this bipolar-oriented triangulation. It includes this spanning tree decorated map that Yuan Zhang talked about. And then up at gamma equal to square root of 8/3, it includes the undirected square root of 8/3 LQG metric, which is related to this Brownian map and Schaefer bijection and so forth. So sort of the general belief is that there's there's this one parameter subfamily of directed LQG metrics which are sort of integrable. And we've been able to cover quite a few of these using our methods. Okay, so thanks for listening.